Welcome to the Boston Echo Boards Review course. Today we'll be going over the aortic valve area calculation. Aortic valve area calculation is one of the most commonly performed hemodynamic calculations in the operating room using echocardiography. However, there are significant confusions, ambiguities, and lack of knowledge regarding the basis, the advantages and limitations of continuity equation and its comparison and contrast with the Gorlin equation. So in this lesson today, we'll have a detailed overview of the basis and limitations of the continuity equation and compare and contrast it to the Gorlin equation. Enjoy. Well, the first question to ask is, why is it important to know all this? With the percutaneous interventions becoming more common, the accuracy of the aortic valve area calculation has received significant attention. Now, accurate measurement of the left ventricular outflow tract is a critical component of the calculation of the aortic valve area and is the greatest source of error. Availability of three-dimensional echocardiography has demonstrated the variability in the structure of the LVOT and its impact on the calculation of the aortic valve area through the left ventricular outflow tract area calculation. Similarly, accuracy of the Doppler velocity profiles across the LVOT and aortic valve area can also significantly impact the accuracy of the calculation of the aortic valve area. As we all know that the degree of systolic dysfunction can impact the opening of the aortic valve area, and now we appreciate a condition such as a low-flow, low-gradient aortic stenosis. Therefore, it is not uncommon to encounter discrepancies in the operating room with consequent clinical and echocardiographic dilemmas in decision-making. The discordances in areas calculated in the cath lab as well as in the operating room are often attributed to the difference in methodology of aortic valve area calculation and estimation of the effective orifice area versus the geometric orifice area, and the peak estimation of gradient using echocardiography, which measures the instantaneous peak gradient as opposed to the cath lab gradient, which is non-instantaneous, and also the difference between peak and peak between the LVOT and the ascending aorta. So there's a lot of differences between the way the areas are calculated, but are they big enough to impact the discordance to the point that the clinical decision may change? That remains to be determined. Therefore, we've reviewed the hemodynamic principles of the continuity equation as well as Gorlin equation and seen whether these areas and the discordances in these calculation of these areas are due to these methodological differences in the assumption of constants and flows in the LVOT and across the aortic valve. Let us first go over what is the geometric or the anatomical orifice area of the aortic valve and see what are the principles of its accurate determination and what are its limitations. Planimetry of the aortic valve in the mid-esophageal aortic short axis view provides the anatomical orifice area. That's the area of the identified at the tips of the aortic valve leaflets. Now, the assumptions are that you have identified accurately the systolic ejection phase, that's the maximal opening. The edges are clearly delineated, and we have accurately planimetered the edges without any parallax error. Now, the assumptions inbuilt into this are that the aortic valve is planar. Well, it is not. The aortic valve is fixed. Well, it does not, because it does move with the translation motion of the heart. And the edges that we have identified are the actual edges of the aortic valve, as you can see in the graphic animation on the right side. I mean, when we cross-section, the projected area will appear as an edge when you look at it on FOSS. And finally, that the maximum systolic ejection phase has been identified. These are the four major assumptions of it. Now, the use of three-dimensional echocardiography has improved the delineation of the edges and the placement of the calipers and the planimetered tracing at the identified edges, which are accurately the edges, but it does not entirely eliminate the possibility of an error, particularly in valves that are heavily calcified and fibrosed. And as you can see, depending on where you cut the valve, like at this one, cut at the tips of the leaflets, is being on the up top left is 3 square centimeters. You move a little down in the middle, this is 2.75, and then you move further down and it's 3.5 centimeters squared. So it really is a function of how accurately you are able to identify and section the edges of the aortic valve leaflets for an accurate estimation of a geometric area. So the major issues with planimetry are that it correlates poorly with other methods. It's not reliable when the valve is heavily calcified, and that's when you really need to have an accurate area calculation, and does not account for the temporal variation in aortic valve opening, which means if you don't identify the maximal opening, you may miss you may misdiagnose aortic stenosis or overestimate aortic stenosis. And finally, it identifies the anatomical orifice area, whereas physiologically, the effective orifice area that we shall discuss next is the most important thing. The planimetered geometric area of the aortic valve represents the geometric orifice area of the valve. The effective orifice area is represented by the area of flow contraction beyond the stenotic valve. Now, due to principles of flow dynamics, high-velocity jets demonstrate significant flow contraction up to almost about 29 to 30% beyond the point of stenosis. As a result, the smallest area occupied by the flow is beyond the point of anatomic narrowing of the orifice at the vena contracta. That's the point of flow contraction. As in aortic stenosis, the vena contracta is beyond the aortic valve on the ascending aorta side of the valve. And the maximal pressure drop, as we can see, between the LVOT and the ascending and the stenosis actually tends to happen at the point of vena contracta when it achieves maximal flow contraction and maximal velocity. The gradient that we measured with continuous wave Doppler is reported as the peak transaortic gradient, that is the gradient between the LVOT and the vena contracta. Therefore, the area that we measured with continuity equation represents the area of the flow contraction of the vena contracta, that is the effective orifice area and the true aft load burden of the aortic valve. This peak gradient is different than the peak-to-peak gradient that is measured in the cardiac catheterization lab, that is a non-instantaneous gradient, and also is not temporally occurring at the same time. Therefore, there's a methodological difference in the reporting of the peak gradients between the one we measure in cardiac cath lab and the one that we measure with continuous wave Doppler using echocardiography. So now let's get to the Gorlin's equation. Gorlin's equation is derived from principles of fluid dynamics and basically derived from Torricelli's law, which is a theorem in fluid dynamics related to speed of fluid flowing from an orifice. The law states that the speed of efflux of a fluid through a sharp-edged hole at the bottom of the tank filled to a depth h is the same as the speed that a body, in this case a drop of water, would acquire falling freely from a height. Now, there were significant differences in what was predicted flow and what was the observed flow, and they were attributed to a coefficient of discharge that took into account the viscous losses and the reduction in the velocity or the speed of the fluid based on reduction in the height of the column, as well as flow contraction, that is formation of vena contracta, which means the narrowest portion of the fluid flow being formed a little distal to the hole. And that forms kind of the basis of continuity equation as well as Gorlin's equation. So the original formula proposed by Gorlin and Gorlin in 1951 was derived from Torricelli's law and was described to measure the area of a stenotic mitral valve. It was based on a derivation of Torricelli's law, which implied that an area occupied by flow at any given time is equal to flow divided by the velocity of flow. Now, in 1951, it was not possible to describe the flow or measure it accurately. So the total cardiac output divided by heart rate times the systolic ejection period was believed to estimate the stroke volume at given moment in time. And mean pressure gradient across the valve was estimated to be the flow across the valve. Now, the contraction coefficient, that is the degree of contraction of flow when it passes through a stenotic valve, as well as the viscosity coefficient, which is loss in viscosity over time, viscosity-related flow changes, were all lumped into a discharge coefficient. We'll get into the detail of how that discharge coefficient affects the calculation of area, and that all accounted for the initial energy losses. And so that was the initial Gorlin's equation. Like we've discussed in the past, that the Gorlin's equation was originally discovered to calculate the mitral valve area, based on Torricella's law that the area occupied by flow at any given moment in time is equal to the flow divided by the velocity of the flow. Now, to account for the differences in what was measured and what was the actual area, a discharge coefficient was introduced into the calculation. Now, the discharge coefficient consisted of a contraction coefficient, that is the degree of contraction of flow, as well as the viscosity-related inertial losses, and that was the viscosity coefficient. Now, the viscosity coefficient was found to be negligible, was assumed to be 1 and ignored in the equation, but the discharge coefficient was mainly consisted of the contraction coefficient, and it was believed to be a 0.85% flow contraction that accounted for the observed effective orifice area that was smaller than the geometric orifice area. Therefore, the contraction coefficient was incorporated in the equation to account for the flow contraction and equate or equilibrate the effective orifice area that was measured to the geometric orifice area that was the actual area of the valve. Now, important thing is that the 0.85 of contraction coefficient was originally developed for the mitral valve, and was also developed, was developed for the pulmonic valve, that is 0.85. However, a contraction coefficient for the aortic valve was never developed, and the one that was supposed to be developed for the pulmonic valve was extrapolated and adopted for the contraction coefficient of aortic valve area calculation as well. So now let's get started with the more complicated portions of the Gorlin equation and try to understand what exactly is measured by a Gorlin equation. Is it the geometric orifice area, or is it the effective orifice area? Effective orifice area being the area of the vena contracta, and geometric orifice area as the true anatomical area of the aortic valve. So as it stands, the Gorlin equation in its final form is designed to measure the geometric orifice area, and is derived as Q, that's the transaortic flow. The contraction coefficient signifies the degree of contraction of flow when it comes out of the stenotic valve, and believed to be 0.85. Viscosity coefficient corresponds to the viscosity-related inertial losses and is believed to be 1 and negligible. The gravity-associated acceleration is 980.67 centimeters square. And lastly is delta P, which is the gradient between the aortic valve and between the left ventricular outflow tract and the ascending aorta. So let's get to step 1. As the first step in the process, the pressures, that is the gravity-associated pressures, as well as the gradient across the aortic valve is converted from centimeters to millimeters of mercury. And it turns up to be the gravity-associated acceleration is 51.6 times the contraction coefficient times the viscosity coefficient times the gradient. Now, the contraction coefficient we all know is 0.85, and the viscosity coefficient is 1, is negligible. Now, if we finally solve the equation, it would turn out to be the flow divided by 51.6 times 0.85, that's 44.3, times the gradient across the aortic valve. And if you were not to incorporate the contraction coefficient of 0.85, the area would be flow divided by 51.6 times delta P. Now that's the most important part over here. Because in situation number 1, when we incorporate the contraction coefficient, what we have done, that we actually measured the area of the vena contracta, but we know that there is a flow contraction to a degree of a coefficient of 0.85. So the area is increased by 0.85 by having 0.85 in the denominator, and therefore the area that is obtained for the effective orifice location or the vena contracta is corrected or increased to correspond to the geometric orifice area. So if the contraction coefficient is incorporated, the effective orifice area or the vena contracta area is increased to correspond to the geometric orifice area, assuming that there is flow contraction. However, if we do not incorporate the contraction coefficient, then we either assume that there is no flow contraction, or this is the actual area of the vena contracta, and that is the effective orifice area of the aortic valve is measured, which is not corrected through the geometric or to become the geometric orifice area. So therefore, incorporation of the contraction coefficient corrects the EOA to correspond to the geometric orifice area. But if we do not incorporate the contraction coefficient, assuming they're both equal, then we measure the effective orifice area, that is the area of the vena contracta, with the Gorlin equation. Now let's go over the continuity equation finally. It's based on multiple assumptions of geometry and flow, and also based on principles of fluid dynamics. Assumptions are that you have measured the diameter of the LVOT accurately. LVOT is a perfect circle, so a single linear measure provides the area of the entire circle. You have accurately aligned the Doppler. You've obtained the peak velocity. The flow in the LVOT is laminar, and you've obtained the pulse wave Doppler exactly at the same location where you measured the LVOT diameter, and it's a smooth and a straight profile of the pulse wave Doppler. These are the assumptions. Now, if you go over and take a look at it, it's based on continuity principle, which means the flow is continuous in the absence of a shunt between two contiguous points. So therefore, cross-sectional area of the LVOT times the velocity time integral at the LVOT should be equal to the flow across the aortic valve, and therefore this whole equation can be solved for cross-sectional of the aortic valve, which is the flow through the LVOT divided by the peak velocity through the aortic valve. Now, this is flow divided by the peak velocity. Sounds familiar? This is essentially the same as the Gorlin equation. It's not any different from Gorlin equation, which means area occupied by flow at any given moment in time is equal to the flow at that given moment in time divided by the peak velocity across that point. When you go over the continuity equation, cross-sectional area of the aortic valve is equal to flow divided by the peak velocity. So therefore, Gorlin and continuity equation are essentially the same principles of fluid dynamics and not any different. And whether or not they measure the effective or the geometric orifice area, we'll get to that in just about a second. So in the final analysis, we'll compare and contrast the Gorlin equation with the continuity equation and the differences between geometric and effective orifice area. Geometric orifice area being the anatomical area of the aortic valve, and effective orifice area being the area of the flow contracted fluid, which is a little distal to the contracted aortic valve, albeit being a little smaller than the actual or the geometric area. So since continuity equation measures the highest gradient, which is between the LVOT and the point of the vena contracta, when we use the continuity equation, we measure the effective orifice area, that is, the orifice area of the vena contracta. When we are using Gorlin's equation, and we ignore the contraction coefficient, and we assume that the effective orifice area is equal to the geometric orifice area, and do not assume any flow contraction to happen at all, we measure the effective orifice area. However, in Gorlin equation, when the contraction coefficient is incorporated, and we assume that the flow contraction has happened, we increase the effective orifice area that is obtained by a factor of 0.85 to match it or to correct it to match to the geometric orifice area. Therefore, in the final analysis, the Gorlin equation can be used to estimate the geometric orifice area by incorporation of the contraction coefficient, or the effective orifice area if we ignore the contraction coefficient. And the continuity equation always measures the effective orifice area. And it has been shown that for any given area in a pulse duplicator and in vitro model, the Gorlin equation with incorporation of contraction coefficient provides an area 1 to 2% greater than the continuity equation. Also, both are flow dependent, therefore with increasing flow and pressure, there is a linear increase in the calculated valve rate, about 20% for aortic valve and 35% for mitral valve, implying that they measure the effective orifice area and not the geometric orifice area. Therefore, both methods can result in aortic valve areas that are erroneously smaller in low flow states and with depressed ejection fraction, and paradoxical low flow, low gradient aortic stenosis with ejection fraction. So essentially, by incorporation of the contraction coefficient, we are increasing the effective orifice area obtained with the Gorlin equation to match the geometric orifice area. They are also dependent on the same flow principles of Torricelli's theorem, and therefore subject to all errors of flow-dependent variables that are incorporated in the equation. I hope I was able to give you a broad and an in-depth analysis of both the Gorlin and continuity equation, and you can understand the principles of the calculation of aortic valve area. Thank you.